All right, good afternoon, everyone. Thank you for joining us. This is a LEAP lecture in climate data science, and we're happy to welcome today SALVA, RÜHLING, CACHAY from UC San Diego. Just a quick introduction of Salva. He's a fourth-year PhD student at UCSD. He's working on generative modeling and AI for science. He's working with Professor Rose Yu and Professor Duncan Watson-Paris. And his research focuses on developing innovative AI solutions for weather and climate modeling, trying to advance our understanding and prediction of Earth's complex systems. He's collaborated with folks like Jump Trading, NVIDIA, and the Allen Institute for AI. And Salva, thank you so much for taking the time to join us today. Whenever you're ready, please unmute, share your screen, and we're happy to hear your presentation. Thank you.
Of course. Yeah, thank you so much for the invitation. Wait, I'm trying to screen share. Okay, yeah, you see my screen, right? Perfect.
Yes.
Yeah, I'm very excited to be able to have the opportunity to talk to you today about my research so far in my PhD, which has focused on yeah, generative modeling for weather and climate applications, especially forecasting and emulation problems. And we'll start with some motivation. Like, why do we want to use Gen AI for weather and climate forecasting or emulation? And what are some limitations of existing methods if you may want to apply them? Or if you might want to take off-the-shelf methods from other fields to this set of specific problems in weather and climate, and what are potential limitations there? I should say at any point, please feel free to interrupt me with any questions during the talk, or you can ask me later, as you prefer. And so to answer some of these, well, motivational points and limitations, I'll start introducing a first paper called diffusion, which is a first attempt at I guess, specializing diffusion models, which is a specific type of Gen AI, to forecasting problems, especially forecasting problems in chaotic systems. And then we'll look at an application of a follow-up paper of this framework to global climate model emulation. And then lastly, I'll also introduce my most recent paper, elucidated rolling diffusion models, where we look at the problem from a very similar angle and with similar motivations and ideas, but then choose a different, slightly different solution that has its own benefits too, and we'll see its relevance for weather forecasting, for a weather forecasting problem. Yeah, so let's start with some motivation. So one reason why Gen AI is very interesting for weather and climate is because it allows you to ensemble your model. So you can do ensemble forecasting or ensemble simulations, and through them you can quantify uncertainty. And so that's very important for many applications where you want to model full distributions of the future and not just point predictions. And a common limitation of many existing models in these topics is that they're deterministic. So they only give you point predictions. And so you can't use them for uncertainty quantification. But what's more is that they're often also blurry and unphysical in the long range in particular. And that's because they give you a point forecast and they are trained on losses like mean squared errors. They are only able to predict you the conditional mean in the future. And if you roll that out many time steps into the future, those become quite blurry and unphysical. And you can see this, for example, in this figure on the right from one of such deterministic models from recently, where the predictions are on the right column, and you can see that they're simply much more much blurrier than the ground truth, especially when you look at 1 month ahead predictions. So that's that. And then another common limitation is that many of these many existing approaches are autoregressive, and in particular, they usually follow this framework of taking one previous time step. So let's say we want to do forecasting. You take one previous time step and you train the model given that previous time step, your initial condition, to forecast the next time step, or to predict the next time step. And then that's your training, your training algorithm. But then during inference, during evaluation time, you actually want to run them for much longer. Like you might want to do a weather forecast up to 15 days ahead, or a climate simulation for 10 years into the future. And so if you do that with your autoregressive model that has been only trained to see one or maybe a few steps into the future, you'll accumulate errors, and you have this divergence between training and inference. And that's something you see come up in a few models, like the one here in the top right, that just long-term unstable and gives you and produces artifacts in the long term, especially over polar regions, for example, in this case. And then another very important limitation is that physics-based models in general tend to be quite slow or quite compute expensive, and that's one of the main motivations why we might want to consider data-driven emulators of these physics-based models, right? Because they would be much faster at doing the same things. But then, if we look at possible ML methods, diffusion-based methods, diffusion models have been quite successful, and so many people want to use them for these tasks like emulation. But the problem with them is that they are quite slow at inference time. So that would make it that presents a bottleneck. And here we show an example from our spherical diffusion paper, where we are trying to do climate model emulation over very long time periods. And so we want to simulate the climate, the atmosphere of the climate of the atmosphere for up to 10 years into the future. And that's at 6 hourly resolution. So that's a lot of time steps that we're predicting with all these models. And the physics-based model that we're emulating takes almost 80 hours to produce this whole simulation trajectory of 10 years. If you were to apply if you were to naively apply a diffusion model to this problem, you would cut down the time to around 30 hours, but you wouldn't cut the time by a lot, right? Which is one of the main goals in emulation. And then if you use the approach that I'm going to introduce later on, you can cut down the time to 3 hours. So that's already a 25x improvement in runtime over the physics-based model, which is now quite significant. And you can take that even further with a deterministic model, but obviously a deterministic model doesn't give you the uncertainty quantification and ensemble possibilities that our model can give you. So those are a few common issues we want to solve. And then, because as I was saying, diffusion models have been very successful in practice for many data modalities, in particular images, we are very motivated to think of how we can use them, but at the same time solve some of the problems that we see when we naively apply them to these problems. And the main source of inspiration here is that is simply that all these the diffusion models were originally designed for static data, like images, so data that doesn't have a temporal dimension in it, and so the way they work is that they learn a mapping from pure noise, from a very pure prior distribution, to a very to your data distribution at the other end. And so essentially, you can think of having your data distribution being noise over multiple diffusion steps. At each time you add more noise to your data. And your model learns your denoiser network learns the reverse process of going from noise to data. And during sampling time, you need to go through all these intermediate time steps, which is why it's so slow at inference time. But in particular, you can see that there's some kind of notion of time here, right? It's just not, we have this whole process between Sn and S0. Just it's some diffusion time and apostrophes, and not really the physical time we might care about in forecasting or emulation problems. And so that's why we ask in essentially the rest of the talk, how can we design an efficient diffusion model that really exploits the temporal dimension of the data that we'll be using. And the first attempt in my PhD to do this was this paper, diffusion, together with some great co-authors at UC San Diego. And yeah, I'll go quickly over the key ideas on a high level and then look at some applications of that. So here we have the same image again from the standard diffusion models and how they operate. And our key idea here is just that we want to couple this non-physical diffusion steps with the physical time steps of the data that we're using. Like, that could be the weather at multiple different time steps in sequence. And that means that now, instead of starting from pure noise, as in a normal diffusion model, we're now starting from data, actual data, or the initial conditions at some time step t. And instead of ending at the clean data, we still end up at clean data, but at a future time step t plus h. And that the structure then, or this process then also goes over some intermediate time steps t plus I in the middle. And so that's at a high level how we think of it. And the cool part is that if you do it this way, you're able to use many of the advances from diffusion models for our, I guess, rethought temporal diffusion model called diffusion. And one of the main advantages here is that because you don't need to learn how to go from noise to data anymore, now you're learning forecasting, right? How to go from time step t plus h. You're able to train your models much more efficiently and also sample from them more efficiently, because it's an easier task to go from data time step t to t plus h than learning how to go from pure noise or a lot of noise to clean data. That's a very, very non-trivial mapping to learn. Yeah. Oh yeah, sorry, I should mention that one important consideration here is that for a normal diffusion model, you know how to do this forward process of going from data to noise, right? How to add Gaussian noise to your data. It's easy to just sample from some random generator. But in our case, we don't know how to go from time step S0 or any future time step to a past time step. At least we don't assume that you're able to do that, and that you know how to do that. And because of that, we need to train another neural network that takes that from the future to the past, but condition on time step t, and that's why this model becomes an interpolator. So we'll have to train a model that, given time step t plus h and t, returns you any of the time steps in between. And that will take the place of the forward process in our diffusion model. And if we have trained this interpolator and the forecaster, which takes the role of the denoiser network in a normal diffusion model, then we can use them jointly to produce forecasts or future predictions, like in this diagram. So we start from some known state, initial conditions at time 0, and then we forecast with our forecasting denoiser network multiple time steps into the future, in this case, to time step 3. And giving time step 3 and the initial condition, our interpolator will take us back to time step x1. And then given x1, which is a little bit more in the future than x0, we'll refine our forecast with the forecaster of x3. So we'll keep forecasting x3, but every time we'll be interpolating slightly closer to it. And so that's why each forecast of x3 will be refined at each step and improving. This is a sampling procedure of our method, and it mirrors the way a diffusion model would work, because a diffusion model would go from pure noise to data and then noise it back to some diffusion step in between, and then denoise again completely, and then add again noise, but less noise than before, and so on. So that's why we use some diffusion sampling algorithms for this framework. Now, are there any questions on this part? Yeah, sure. I see some small hands in the screen.
Thanks, Salva. This is Bjorn.
Oh,
1,
cool.
2, 3,
Hi,
they
Bjorn.
are the physical time here. Is that right?
Yes, exactly. This is a
Okay.
physical time. Yeah.
Thanks.
Yeah, good question. Yeah, then the important point is that we couple the diffusion time and the physical time in our framework. Yeah, so they become the same.
Salva?
Yeah, sure.
I had a question regarding the mathematical model, how you're modeling things here. So are you adopting a probabilistic approach where you're modeling a conditional distribution of xt plus h knowing xt? And if so, what's the underlying mathematical framework? What are you actually learning in terms of probabilistic modeling in this method?
We're modeling the whole future distribution given xt. So that would be xt plus 1 to xt plus h given xt. And the idea is that we essentially derive our model from diffusion, from a generalized type of diffusion models, which are probabilistic by nature, and we extend them to be also stochastic in our case. And because our model is stochastic too and follows the sampling algorithms from generalized diffusion models, our model becomes probabilistic in that sense too. And but I'll say that the theory behind our model is not as strong maybe as you would have it for a normal diffusion model. There's some, but yeah, I'm skipping it, and that's these slides.
So you're not, if I understood correctly, you're not framing the samples as some. I mean, you're not explicitly learning a score from a given distribution. You're not explicitly modeling a distribution from which you learn a score, right? As in diffusion models.
Right. So yeah, in a normal diffusion model, you're learning the score of your OD or SD that goes from noise to data. We have some theory on that in our paper, that in our case, you can think of it as learning the score from going from, well, one time to the other.
You implicitly model the time dynamics, the physical time dynamics, as some kind of Langevin dynamics, as in static diffusion models. Is this the idea behind it? Or maybe we can talk about this later.
Yeah, yeah, happy to talk about it later. But yeah, the idea is to model the temporal dynamics with a diffusion derived model.
Thanks.
I see one more from Francesco, unless there's one in the room.
Yeah, hi,
Right.
Salva, Francesco here.
Right.
I was wondering, the time step 3 that corresponds to the physical time step is generalizable to any time step, or did you try
Y-
different
Yeah, this
configurations?
is a diagram, and in practice, you can choose your forecaster to predict any lead time you want into the future. So that could be 10 or 5 or so on. In our experiments, we used mostly 6, 6 or 16, and depending on the data set and problem. But yeah, it's flexible.
Okay.
Just you need to train both models for the same horizon, both
Yeah,
interpolator and forecaster.
and I guess it also depends on the application, because if you are working with the forecast, with weather forecast or climate prediction, so it can change according
Mm-hmm.
to your needs. Okay, thanks.
Yeah, you're right. Yeah, it's very dependent on your data. So if it's very, very hard to forecast 20 time steps into the future, then maybe you want to choose your horizon a bit smaller to make the task easier for the forecaster. So that's why for the climate application that we'll see in a sec, we did 6 time steps, horizon of 6. But for maybe less challenging cases like Navier-Stokes equations, we use 16. Sorry.
Thanks.
Sure.
Sorry, could I ask a follow-up question on that? So I'm
Yeah.
not sure, when you say like, would you then like be able to auto regressively roll out? Like, is this like kind of like a stabilizing step, and then you can still move forward from X3 to go to a new?
Yeah, that's a very important question. You're right, exactly. So this is after you've done the last forecast of X3, you can restart this whole procedure with X3 as your new X0, and then you auto-regressively repeat this whole thing until the last time step you want to predict. Yeah, that's what we do in practice. So the model is learning, I guess, some temporal interactions on a small window of size h. And beyond that, you need to apply it autoregressively.
And do you find that's more stable? I guess this just like reminds me of like if you're doing an implicit method to solve something versus, or
yeah, we found it to work quite well, and we have in the climate application it was stable for 10 and 100 years at 6-hour resolutions.
very cool. Thank you.
Yeah, sure. Cool. I'll continue, but yeah, let me know at any time if you do have questions. Cool. So the first. In this first paper, we applied it to sea surface temperature data and Navier-Stokes fluid data. And yeah, I guess you'll see one of these tables that are very common in machine learning papers, machine learning conference papers. We're trying to show that our method diffusion performs quite competitively against, at the time, a very strong video diffusion model, MCVD, while being much faster. And then it does also quite well against other potential ways of making stochastic predictions like input perturbations or applying dropout on your model, which are simple but work to some extent too. And then we have a video of our model, how it essentially models these fluids over up to 64 time steps into the future, and it was trained on windows of 16. Yeah, so this was quite promising, but I guess the original goal for me was to apply this to weather and climate data. So it's more challenging, but also more interesting data, and that's how this follow-up paper spherical diffusion came to light, where we extend our previous idea on diffusion to a climate emulation problem, and we need to change a few things or add a few things to make it work well in practice. Yeah, and Oh yeah, and we got the best paper award at ICML and machine learning for air system modeling last year, which was co-organized by LEAP. So that we appreciate that a lot. Cool. So in terms of what problem we're trying to solve here is, I said, climate emulation. So we assume that we have some climate model, or in this case, atmosphere only model, FV3GFS, from which we have simulated a lot of data at 1 degree. And then given all that data, we want to train an emulator of this climate model, of this physics-based climate model that produces the same distributions of the atmosphere, but at much lower computational cost. And this was first introduced, the problem or this data set was first introduced by this paper ACE at the bottom. And we are trying to improve on that emulator on the same data and same problem setup. So we model the atmosphere, so that's multiple variables across the height of the atmosphere, temperature, humidity, and so on. And we force them by annually repeating solar insolation and sea surface temperatures. This is important because that means that we're not yet modeling global warming scenarios. We're modeling a more simple climate, more simple climate prediction problem, because the forcings are annually repeating. But for now, it was already quite challenging on its own. And then we train our models to predict up to 36 hours into the future. And then we evaluate them on rollouts of up to 10 or 100 years into the future. And so this poses a big challenge in terms of stability and also fidelity in terms of how close these simulations are to the simulation from the climate model that's underlying it. And stability is an issue because, as we saw before, many ML models that have been trained on short windows or a few, or just, let's say, 6 hours only, tend to be unstable when you roll them out for a few months or years maybe. And so that was one of the key issues here. I'll very briefly just say what we did differently than in the diffusion paper. So the main difference here in our application paper is that instead of using the architectures that we used in the previous paper for the interpolator and the forecaster network, we now use SFNO, a spherical Fourier neural operator architecture, whose network topology is shown on the right. And we essentially combined both frameworks. And that was just very crucial to get the results that we got, that we'll see in a sec. And that's because the SFNO architecture is simply more appropriate to model the Earth compared to the unit we were using before. It's more, it has some very good inductive biases that allow it to be stable in the long term and reproduce the climate distribution that we want. Cool. So then I'll go over to some of the results we had. I thought they were very exciting because in climate emulation, I said you want to reproduce the distribution of your climate model that you're training on. And this climate model, and because we have different ensemble members of the climate model, so different trajectories of 10 years into the future, we can compute some kind of reference RMSE on the climatology of those different trajectories. Climatology is the time mean over the 10 years. So we can look at how close those ensemble members get to each other in terms of RMSE and compare it to what our emulators achieve on the same 10-year rollouts. And what we see here for one of these variables that we predict, total water path, is that our model gets much closer in terms of RMSE. and bias, then the main baseline or the next best model, ACE, in this case around 2 times better, but for some variables it could go up to 4 times better. And so it gets much closer to the reference climate model, giving us bringing us closer to be using these climate emulators in practice. I should say that while there's some more quantitative evaluations in our paper and later slides, if in the appendix of these slides if you want, there's still a lot of work to be done on evaluating these climate emulators, these data-driven climate emulators, more comprehensively. Like in this paper, we look at some fairly coarse metrics, like how well do we reproduce the climatology or the variance over the 10 years. But of course, there are a lot of more interesting phenomena to look at and check that they are reproduced correctly in the emulators. Yeah, I also wanted to show you an example simulation from our models. So here you have this is over 10 years for the surface wind speed variable, and you have the one trajectory from FV3GFS, our climate model that we're training on, and then 2 different sample trajectories from spherical diffusion. And first of all, you can see that they seem quite realistic compared to the climate model. You don't see any artifacts at the poles or in general, at least not obvious ones. And secondly, it's stable. Even if you go to the very end of this, you'll see that the predictions are still meaningful. And so those are some very crucial properties of any climate emulator. Sorry, I got out of the full window. Cool. And as the last result, we then went further than the 10 years we did in this in our quantitative evaluation, and looked at 100-year-long rollouts. So here we didn't have ground truth to compare against, but we wanted to check first that it's stable, and secondly, how well it may be, whether we see any artifacts, which we saw in the ACE model, especially for pressure down here. For example, you see some spikes in the global mean pressure field that are unexpected. And those are not seen in our model, giving us, again, a bit more confidence in that it's emulating the climate model better. To summarize, so why is diffusion useful? Mostly because it can produce you some very competitive and stable probabilistic rollout forecasts or simulations, even when compared to quite strong video diffusion models. Something we didn't look at is that you can also use it for temporal super resolution. So increase the resolution of your simulations compared to what you trained on. And then very importantly, it has a much lower runtime than standard diffusion models, and it has also some fairly nice memory complexity if you compare it to video diffusion models. But there are a few limitations, in particular, as I was mentioning before, you need to train 2 neural networks now, not 1. So that just takes more time, maybe more hyperparameter tuning. And it also is not as connected as some other diffusion models to the foundations of diffusion. Because we removed the Gaussian noise part of it in our framework. And that has some disadvantages we'll see in the next paper. But yeah, before going to the next and last one, I wanted to ask if there are any questions before proceeding. Sure, I see one.
Do you think it's still a very efficient architecture in comparison to video diffusion models that we have nowadays? like, for example, pyramid flow or any of the other things that come out that take like a sort of like a multi-scale temporal spatial approach?
Yeah, that's a really good question. So we haven't compared it we haven't kept comparing it to the most recent video diffusion models. And yeah, so I guess I don't know for sure, but I do think it's still quite competitive to some very strong diffusion model baselines. I'll show a few in the next paper where we compare diffusion to some more modern diffusion methods, and it does still quite reasonably while being much faster.
That makes sense. I guess your key innovation, this like multi-step temporal sort of correction that you're doing is complementary to any kind of efficiency that we get through a multi-scale spatial approach.
Yeah, for sure.
So maybe that's
those
also
are probably
good to note.
Yeah, those are probably complementary. Yeah.
Cool. Thanks.
Yeah, of course. Thanks for the great questions. Nice. So I think I'll proceed with this. My most recent paper, elucidated rolling diffusion models, which I'll be presenting at NeurIPS in December this year in San Diego. I hope to see some of you there. It's quite local for me. And this was started at an internship at NVIDIA the year before last year. And we are looking at the same problems, same types of problems, and similar ideas, just I guess a different approach at solving the problems in a different way than what we did in diffusion. So to start again with some motivation, I want to compare here a few different ways you could use a diffusion model for forecasting specifically. So the most straightforward way of applying an off-the-shelf diffusion model would be the what you see on the top row. So that's what we call an autoregressive single-step diffusion model, which given a previous time step predicts you the next one, and the next one, and the next one giving the past one, and so on. And that works quite well in some cases, like for example, GenCast is following this paradigm for weather forecasting, and it's one of the best models for that. But it has some drawbacks. In particular, at each time step that you want to predict, you need to do the full sampling from pure noise to clean data. And as we saw before, that takes a lot of time. And now, if you need to do that for every time step, and you have, I don't know, 100 of those, then you'll be spending a lot of time running your sampling. So that's one main drawback. And the other one is simply that because you're only modeling one or two or three time steps jointly, you're missing out on temporal interactions that might be important to properly model your system. So what people do in video diffusion often is to model a sequence of snapshots or video frames. So in this case, for an example of 3 frames, they model them jointly and they denoise them jointly at once. And that means that the model, of course, needs to be 3D. It needs to model the 2 spatial dimensions in this case and the time dimension. But also because it's kind of like a naive extension of the top row, they apply the same noise levels to all the frames at all times. And so you start from a sequence of pure noise and you land and you predict a sequence of clean data. And obviously that works well for videos, but it can be challenging for data sets where you don't have as much data as is the case in many physics data sets. And that's because already learning a mapping from pure noise to data, as in the top row, takes a lot of time of training time and data. to learn how to go from noise to data. But then if you extend this to going from a sequence of pure noise to a sequence of clean data, that's even more expensive and requires even more data and compute. And so that's a big drawback for using a naive extension of video diffusion. So, okay, and what we propose doing is something called rolling diffusion, where we're, again, modeling a window, a sequence of frames jointly, like in a video diffusion model. But instead of applying the same noise levels to all of the frames in the window, we now apply progressively increasing levels of noise inside the window. So you see always the last frame in the window has the most noise. And the frames before that have less noise. And that's a much more data efficient way of doing this, and it captures the inherent growing uncertainty that that's inherent to chaotic systems, right? The further you look into the future, the more uncertain your forecast would be. Cool, and then let's look a little bit more into how this works in practice and during sampling inference time. So at all times, as said, we model a window of data. In this example of 4 time steps, but it could be any number of time steps. And yeah, we apply increasing levels of noise. So you see this green line on the right that, for the first snapshot applies very little noise, and for the last snapshot, it applies pure noise. So, the snapshot becomes pure noise. And that's what we initialize our model with. So that's what we give as an input to our model. And then given that, it will denoise the whole sequence of 4 frames by a little bit. So each frame becomes slightly less noisy, as you can see in the second row, or in the right. You go from the green line to the I guess purple blue line at the bottom. And so each frame becomes slightly less noisy. And because it's just a slight difference in noise, we don't need as many diffusion sampling steps to do this. In this case, we might use 2 only. Right, and then the last step is that we slide the window of 4 frames, 1 frame to the future. And we do that here because the first frame after this step has been completely denoised, right? Now, the noise level associated with it is our minimum noise level. And that means that we can emit it as a final forecast for that time step. While the other frames still contain some levels of noise, again, they're still progressively increasing. So we need to continue denoising them. But we also add a new frame of pure noise at the most future slot. And with that, we can continue our denoising and rolling the window procedure forever, indefinitely. That's the idea behind it. The methodologically, I should say that this idea of rolling diffusion, of applying frame-dependent noise levels, is not new. That's something that previous papers have explored, in particular this paper called Rolling Diffusion Models. So our main contributions is to integrate this idea of doing rolling diffusion with the very performant elucidated diffusion models framework, EDM, which is, so far one of the best diffusion frameworks, mostly used for images, but in this case, we want to extend it to this, to sequence level diffusion with frame-dependent noise levels. And to do that, we had to extend EDM in many aspects. In particular, the noise schedule now needs to be temporal, right? We need to define how much noise to add here to the different frames, and so the noise schedule that you see here is quite important in practice. You don't want it to add too much noise or too little noise to certain frames. So that's very important. And then there's a variety of small but very important things that we had to adapt or add, like the loss weighting and and a few other things like the architecture that needs to be 3D instead of 2D because now it models the temporal dimension too. And yeah, I won't dive into too much detail here, but if you have any specific questions on I don't know, different components of this method, yeah, feel free to ask and maybe I can answer them. Right. In terms of results, so we first applied it on, again, the same Navier-Stokes dataset as before. Just a very quick slide because here we can compare it to diffusion as well as some very strong modern EDM methods. So EDM is, as I said, one of the best diffusion frameworks right now. And you can see EDM W equals 1 means that it predicts a single time step into the future, and W equals 4 means that it predicts 4 time steps into the future. So that's like an image and a video diffusion model. And then compared to that, our method ERDM performs extremely well. Like around 50% better at the end of the rollout here in terms of CRPS. And also in terms of spread skill ratio, it does quite well in its calibration. So that's very, I think that's empirically a very strong result because you can see diffusion, for example, it performs similarly to the video diffusion model, which is consistent with what we saw before in our previous paper, right? It is still much faster than this video diffusion model, but in terms of absolute CRPS, it doesn't reach the levels of what we are able to get with ERDM. Yeah, and then we also applied it to weather forecasting. Probably some of you are familiar with it, but we essentially take the very standard setup from WeatherBench 2, where you try to model the whole atmosphere at 6 hourly intervals or 12 hourly intervals in our case, and we do this at 1.5 degree resolution. So it's not the highest, but it's not super coarse either. And here we compared our proposed ERDM diffusion method against the EDM diffusion method, which represents the single-step autoregressive diffusion model that you could apply naively to forecasting problems. And it also represents our basically reproduction of GenCast with our architecture, which is based on units, and our data setup, our training setup, compute setup, and all that. But if we control for all of those things and we make those two models very comparable, we see that ERDM is essentially better in most fields and most lead times. While in particular for geopotential Z, you have some pretty strong improvements in some cases up to 10%. And also for the stratosphere, it does quite well on some variables. This is relative to EDM, but not. You might be interested also how it does in absolute terms against some external models like IFS-ENS, which is the best physics-based weather forecasting model from ECMWF, or Neural GCM from Google, and then GraphEFM from a previous NeurIPS paper. So what you can see here, lower is better, is that relative to EDM, IFS-ENS does perform very strongly, and ERDM is sometimes not able to get all the way to the same performance as IFS-ENS, like on 2-meter temperature in particular, but it is able to get quite close for variables like 10-meter winds, or it's even slightly better for temperature at 850 hectopascals, except for the very first time steps. And you also see it to perform competitively against Neural GCM, for example. Not always, but on many variables in lead time. I think that's quite promising, given that there are still a few things that would have to be improved to get optimal performance in our framework, like choosing a better architecture or more compute. In terms of spread skill ratio, where you want to be as close as possible to 1, which means that your model is calibrated in terms of the score, our model does quite well too. It's pretty much comparable to the physics-based model IFS-ENS, and consistently better than the EDM baseline, which is sometimes under-calibrated on especially early lead times. And similarly for neural DCM, which is also under-calibrated on short-range forecast. As a last thing to evaluate, we are looking here at how realistic the forecasts are in terms of power spectra. So what we want here is to reproduce the power spectra of era 5, which is the data set. So that's the ground truth power spectra. And the closer we are to that, the more physically realistic our forecasts are. And so what you see here is that one of these models has some noticeably issues in the high frequencies, so that's neural GCM, which just don't match the ground truth, and that can be problematic if you are looking at physically very realistic model. So here at the bottom, to look a little bit closer and be able to see differences between models, we look at the normalized power spectra, normalized by era 5. So now closer to 1 is better. And what I think is very, very nice here is that ERDM's power spectra are essentially as good as the ones from IFS-ENS. Again, IFS-ENS is a physics-based model. And because it's physics-based, it's physically realistic by design. So being able to be at the same level of physical realism as measured by the power spectra is a very, I think, strong achievement that has been hard to get in many previous papers. So yeah, just want to share this last very nice property of ERDM. Cool. That will be all for my talk. Yeah, definitely let me know if you have any more questions. And yeah.
Hi, thank you so much for this great overview of your last years of work. I'm wondering that in the world of generative machine learning, right, we had GANs, normalizing flows, autoregressive models, and diffusion models. And then like now we've been sitting on this diffusion model train for quite a while. And do you see now emerging trends going to NeurIPS that you think will be starting to take over? If you were to do this, if you were to start doing another work now, and you were told not to use diffusion, which methods do you think would be interesting?
Yeah, that's a really good question. I think there's definitely room for diffusion so far, at least in many applications. Not all, for sure, in particular applications that require speed. But one very interesting framework is flow matching for sure. It shares many similarities with diffusion, but it is said to be faster. There hasn't been much on using flow matching for weather and climate. There's one paper on weather forecasting with flow matching models, which seems to work quite well, but not a lot of stuff. And many of the ideas that you use for diffusion can be integrated back to flow matching because they share many of the same theory and similar properties. So I think that could be quite interesting, like something like flow matching, rolling flow matching models or something like that could be a nice project.
I see. Yeah, that makes sense. Flow matching models do seem exciting. And as a follow-up on that, I'm wondering what your take is on the models that just optimize CRPS without going through the diffusion stops. They just take the L1 or the L2 loss and replace it and learn CRPS instead, inserting again some form of stochasticity through MC dropout or a noise, whatever, conditional normalization layer, like somehow making your model noisy and then just training on CRPS. And then we only have a single forward pass. And I wonder what your take on those models is.
Yeah, so those models seem to be they are extremely efficient by design because, as you said, they only need to do a single forward pass. And they seem to work extremely well for weather forecasting, at least. There hasn't been much yet on other applications, but they might work very well for climate emulation too. I think it's a very good fit for weather forecasting because, well, for weather forecasting, if you're looking at CRPS scores, because now you are training on CRPS scores, and that almost always will give you a better performance with an ML, with a neural network, if you train on the same thing that you're evaluating on the same metric. So I think it's natural that they do quite well. I think it could be interesting to combine that with a diffusion or full matching model. Like you could train them on a CRPS too. And it will be more compute expensive, but maybe that will improve on it will be even better than CRPS models. But they're definitely great choices for many forecasting applications.
Thanks, very cool. I'm wondering, could you just comment a little bit more on the noise schedule for the rolling method? Is that something that is just like a hyperparameter? I would imagine it would be very sensitive to like whatever physical, if you're modeling a physical system, like the inherent dynamics of the system.
Yeah, it's quite important for sure. You're right. Let me maybe share this slide here. So, or to answer your question directly, it's very important, and a lot of tuning went into that, and it is manual to some extent, especially for this hyperparameter rho that I'll explain in a second. But once we found a good noise schedule, it looked like it works quite well across applications. So we use the same noise schedule for both our Navier-Stokes and our ERA5 experiments. So that kind of gave us the confidence that it's somewhat robust here. But obviously, I think if you tune it further, you could probably improve on it. But it is robust to some extent. And maybe let me explain the image. So the noise schedule is defined by 3 hyperparameters: sigma min, the minimum noise level; sigma max, the maximum noise level; and rho, which is controlling the slope of your noise schedule. And by default, if you use, these are all taken from EDM. They're the same there. If you take the default value for rho from EDM, which is 7, then you get the slope in blue. Well, if you get, if you use the one that we propose after doing a lot of tuning, which is the red one, rho equals -10, you get a different slope. And the different slope implies that the noise applied to different frames is slower relative to the rho equals 7 noise schedule. And that just seemed to be very important because we're modeling all those frames jointly. So we're giving them all together as an input to our network. And if they have a lot of noise in them, then it just becomes a harder problem to solve. And it might be proner to overfitting too. So that's one of the issues we saw. But we still use rho equals -10 for both our experimental data sets. You might need to tune some things like sigma max and sigma min are somewhat data dependent. So if you normalize your data to have a 0 mean and a standard deviation of 1, then you can usually go with sigma min equals this. But you might want to tune sigma max to your problem. Like if you have a big range of magnitudes, then you might want to choose a larger sigma max. So that your noise that you apply, your maximum noise that you apply, is able to fully cover your data and fully corrupt it. Does that answer your question?
Yeah, very, very interesting things. I guess it also may be sensitive to the timing of your snapshots as well.
You mean the resolution of the data? Like,
or, I guess like just however you decide like what your time step is between the different segments.
Yeah, for sure. That would change the problem too. Yeah. We haven't looked into ablating that, how it changes if you use different resolutions and times, that would be very interesting for sure. Yeah, I can see that you will have to change a few things.
Thank you. Any other questions in the room?
Yeah, thanks so much for joining, all the great questions. Cool. Have a great day. Bye bye.
Thanks, you too. Bye.